Okay, so this is an oxidation number problem. Please ignore the fact that I have the answer up there because we're going to do that, of course. Okay, so really when you're doing oxidation numbers, you're looking at atoms, okay? So these numbers, the coefficients, they never matter, okay? You can completely ignore those. That's one of the common mistakes people make. Okay, so you have to remember to some degree, you have to have that memorized, your rules for the oxidation numbers. And so what is a pure element? Well, if it's a pure element, then that's like what's on the periodic table, right? And those are all neutral, aren't they? So they would have oxidation numbers of 0, okay? And so for example, H2, that's the pure element, isn't it? And so that's going to have an oxidation number of 0, okay? Right here. This Na right here, that's a solid. That means that that is the sodium metal, right? That's the elemental form. Notice it doesn't have any charge up here. That means it has a charge of 0. So its oxidation number has to be 0. And so one of the ways you can also look at this H2 to remember that, if you don't remember that that's one of the diatomic gases, well, it's 2 hydrogens, right? If you have 2 equally strong things, neither is going to be able to take from the other, right? And so neither of them are going to gain or lose electrons from each other, right? Meaning they'll be 0. Remember, this is an accounting for the electrons, right? Where are my electrons? Okay, so we're going to go ahead and do all of them, even though the problem only asks you for the reactants in this case. We're just going to do them all. Hydrogen only has 2 oxidation states it normally takes up, but oxygen's the easiest one. If you have oxygen, I would always go for the oxygen first, because oxygen, literally oxidation comes from the word oxygen, right? Okay, so oxygen, whenever it's not bonded to itself or bonded to something like fluorine, it's always going to be a -2, right? Because how many electrons does it want? 2 steps to a noble, right? Wants 2 electrons. Electrons are negative, -2. Okay. Hydrogen here, well, each hydrogen would have to have a what charge to give you this that is 0, right? See, this is overall 0. Doesn't have an overall charge, does it? And so these 2 hydrogens together have to balance off that -2 charge. That means both of the hydrogens together would have a +2, right? Should balance these. And that means each hydrogen would have to have a +1, right? Again, it's the number here that I'm looking at, which is the number of those atoms, right? Okay. And so each one has +1 for this hydrogens here. Mm-hmm. It's always like a little math problem. You're always balancing the charges on the atoms to give you the overall charge of the molecule, okay? It's very, very similar to, in fact, it's the same thing that you are doing for the ionic compounds. It's just ionic compounds were whole charge numbers. These are actually partial charges, okay? That's really the only difference. Okay, how about this one right here? So just go with the thing you know the best. So like sodium, what charge does it normally want? Sodium? +1, you got it. Yeah, we look at the periodic table. How many steps to a noble? It's okay. It's totally okay. Yeah. It's honestly, it's morning on a Tuesday. All right, so let me look at oxygen here, and that's normally what? Yeah, -2, you got it. And then the hydrogen is normally +1. We go ahead and look at all these together. +1, -2, +1. gives you 0 overall, right? Got it. And so we're good. Yeah, we got it. And that's it. So if we were going to enter this in down here, we're only doing the reactants. And so we look at sodium as the first one. That's the 0 up here. Hydrogen is the next one. That's a +1 oxidation number. And then the oxygen is -2.
So since sodium was a solid in the reaction, that's what made it 0.
Yes. Yes.
But
So
then when it's paired with other things,
what we're literally seeing here is we have sodium metal. It's reacting with water. And that reaction with water, the sodium metal loses an electron to the hydrogens. See that? So one sodium metal loses an electron to one of these hydrogens. The other sodium metal, that's this 2 right here, loses electrons to another one of these hydrogens. And we get hydrogen gas. Okay? And that's that. Is that making a bit more sense? Okay, I think you're trying to go from top to bottom, and you really just need to go step by step. Take it step by step. There's simple rules for oxidation numbers, and that's all you need to concentrate on. Okay, remember, these are atoms. The atoms are going to change from one side to another. That's actually what a reaction is. Gaining and losing electrons, right? So this is literally just an accounting, like you'd account for your bank account. I lost $5 here, I gained $10 there, right? Okay. So if you have something that's neutral, this is an atom by itself, so whatever charge is up here has to be its oxidation number, period. Okay? Because there's nothing else that the electrons could be on. That's it. So it hasn't gained or lost electrons, it is just, neutral. Okay. This one right here, well, this is with something that would have taken its electrons, right? And so the oxygen has part of the rules that are in the slideshow that I gave you guys, is that oxygen is normally a -2, okay? If you don't remember it, you can look up at the periodic table. Oxygen's on the top right. It's going to take electrons from stuff. And it's 2 spaces to a noble, right? And so the oxidation number for oxygen is -2. Remember that up here is where the charges for the molecules are. So every time, you always have to add together to get this charge up here, okay? And so to counteract a -2 charge, what do you have to do? Well, you have to have +2. There's 2 hydrogens to split it among, so each of them has to have a +1, right? And that's it. You're done. That's all you need for the problem. You now just put those in. That making sense? No problems there at all?
No idea.
Okay. And then you just do the same thing for products. So the next problem in this, I have part E probably. Yeah, you would then do it for the products. We just went ahead and did it all in one. So the products then is going to be, well, if we look at this has an overall charge of 0, right? So this overall charge is 0. And so then we use our rules we know. Okay, so oxygen, that's normally -2, right? If sodium's going to lose its electrons to something, like say a nonmetal, which is going to take electrons from it, right? Then sodium would normally be a +1. How do we know that? We look at the periodic table, we count the steps to a noble, right? Sodium's on the left, it's group 1, that would be a +1. Hydrogen then, well, to balance it out, that has to be a +1, doesn't it? Okay? And so that gives us these numbers here. No, it's actually very simple steps that you just follow and get it, kind of like those structures. Just follow the simple steps. You'll get it right every time. It's not something you have to see big picture first. It's actually easier just to do small picture first and then look at the big picture. And then this is the neutral, right? It's neutral overall. Neither of them would gain or lose an electron from each other because they're the same thing. And so it's 0.
So what about when you get to transition metals, like nickel chloride?
You just figure out everything else. So, which one? Nickel chloride. Ni. Yeah. Transition metals, I need to know what the charge is. Okay, so this one right here, chloride would normally be what? 1 minus, right? There's 2 of them, so that gives you a -2. But the overall charge is 0. And so the nickel has to have what charge to counter that negative? You got it. That's it. Yeah. It's actually the exact same thing as when you did the ionic compound charges. Because ionic compounds, those oxidation numbers are the charges. For covalent compounds, the oxidation numbers are actually partial charges. You don't get a full charge. Yeah, it's actually really quite simple and easy, isn't it? You just gotta, and try not to absorb everything at once.
I think the thing that gets me is like, so if like carbon's like how sodium was by itself, or like carbon, how would want it to be that +1, that's what would trip me up.
Oh.
And so now I'm like, okay, how do I know that it's actually supposed to be 0?
Well, first off, if it's by itself, if there's literally nothing attached to it at all, then it can never be charged. It would have to have this charge up here.
So it has to be connected to something.
Yeah. For it to be sodium plus, 1 plus charge, you literally have to, that is sodium plus, right? That would have a +1 charge. Yeah. Yeah, if you had Cl minus, as we saw before, anyways, be complete. That'd have -1 charge, right? Okay. Sulfur, solid, well, doesn't have a charge up there, so it has to be 0. If it has a negative charge, it would be, that'd have to be aqueous, actually. Yeah, because if it's by itself, you have to put the charge up on top, right? There's nothing to mask it. There's nothing to counterbalance it.
It's almost like, let's say balancing equations, you've got
It's actually, it is the same thing as the ionic compounds were, where you had to complete and balance the little equations. Yeah, each of them's a little formula. It's the exact same thing. It's just in this case, you have covalent bonds. So they're called oxidation numbers. Okay. In fact, the interesting side note to this is an ionic compound. Right here. That's Na plus and OH minus, isn't it?
Sodium hydroxide.
Yep, it is. Notice the oxidation number +1, Na plus. And this one right here is -2, then +1, which gives you the -1. Yeah, and what you use these for is this is a method to break problems down and identify what is losing and gaining electrons. Okay? So then you could identify what's being oxidized and what's being reduced. Yeah. And it's literally a method so you don't have to try to absorb everything at once and try to, work with this moving picture with dozens of things in it. And you can break it individually, one item at a time.